So how do we do this with the serial first approach? Well, unfortunately the runtime can't automatically take care of pipelining, so we need to manually overlap, and we need to manually prioritise too. And actually we need some quite complex code to do this. It's got to prevent data overwrites and manage buffering, as well as making sure everything executes in the correct order. And for all but trivial applications, this is going to become really difficult. It's also necessary to introduce parallel constructs all throughout your sequential code, and that's going to make it harder to browse and maintain. And everybody needs to be a parallel programmer to understand it. So what does Blueprint and the parallel first approach do for you? Well, Blueprint has fully flow controlled reentrancy, and what this means is that from within the circuit you can specify how many times execution can overlap. You can specify priorities for the jobs. And the runtime manages all of this transparently. So it's really easy for the programmer to use pipeline parallelism. All you've got to do is change some numbers. There's no worries about data overwrites. The runtime isn't going to schedule a job until both of its inputs and its outputs are ready. A really important benefit is that your existing sequential code remains intact. So because your existing sequential code is called by the parallel infrastructure, it doesn't have to change. And that also means that you can keep it in your favourite language. There's no need to litter your sequential code with parallel constructs. It just runs sequentially. And also we have a separation of concerns. So the Blueprint components are only concerned with describing parallelism, and they do that very well. But equally, your sequential source code is then only concerned with describing sequential activities, which it does very well at. And because we're only concerned with dealing with parallel issues in the Blueprint components, the description is contiguous. And that means that it's easy to analyse for concurrent bugs, deadlocks, race conditions, that sort of thing. And it's pretty easy to understand as well. With a bit of practice you can take a look at a circuit and pretty much understand what it's doing. It's very easy to browse because everything's connected, so you're not searching for things. And all of these things make it easy to maintain. And so if we compare the latent concurrency profiles side by side for the two different approaches, you can see why the task manager output was so different. On the left here we've got big spikes in latent concurrency, but we don't make use of that, and then later on we end up with underutilization. On the right hand side in the Blueprint implementation you can see that we've smoothed these across, and so by using this pipelining approach we've achieved a high latent concurrency all the time, even with 16 cores. In the example we've looked at, we've seen that as the core counts start to increase, particularly to 8 and 16, the difference between these two approaches is really quite significant. And I'd just like to draw your attention to this graph produced by Intel, because what they describe as the many-core era with massively parallel applications is not too far off in their view. Another important point is that the SMP architecture is already starting to face some scalability issues, even at 8 cores, to do with bus bandwidth. Now, Blueprint enables SMPs to be used for longer by facilitating efficient cache usage, and that involves trying to run jobs that have large amounts of state on the same core each time to avoid shifting that in and out of main memory. But eventually there's going to come a point where the SMP model isn't sustainable anymore, it just won't scale. And Intel have certainly been talking about next generation cluster on chip architectures, where depending on which nodes are communicating, it might be by reference or by message passing. Blueprint is already ready for these architectures because it isolates the programmer from the underlying topology, so your application code wouldn't change. So in conclusion, although the bottom-up approach may suffice for a small number of cores and provides a quick win in the short term, it runs into many difficulties as the core count increases, and application complexity must rise significantly to liberate all the potential concurrency. Blueprint's top-down approach takes the strain off the programmer by retaining much of the application's existing serial code unchanged in any language, providing runtime facilities to overlap and prioritize jobs, thereby making best use of available CPUs, and providing a contiguous parallel description that is much easier to work with than dispersed parallel constructs used by bottom-up approaches. Thank you.